Good afternoon, everybody, and welcome to the faculty lecture series where we feature Jingquan Yu. Many of you don't realize, but Jingquan's name actually means gold, power, and excess of all of the above. And this might be particularly surprising to anybody who knows Jingquan because he is the quintessential example of a self-made man. He was born and raised in a very rural area, underdeveloped at the time, the Zhejiang province in China, shown here on the map. And what's impressive about his upbringing is that his mom was a farmer, his dad was a miner, and he had to make all his food, clothing, water, energy, and basically learn how to live without much of anything. Although this area was very beautiful and very serene, at the time it was very underdeveloped. So even to buy something would be a 40-kilometer trek. His life took a different turn when he turned 12, and government officials found him and his talent and realized that there was something very special there. So they moved him to a boarding school. And then, after that, he went to East China Normal University, which is just outside Shanghai. And he also did undergraduate research at the Shanghai Institute of Organic Chemistry. Here's his actual graduation photo I was able to locate. This is Jingquan Yu back in 1987. You may not be able to recognize which one he is, but I've done the hard work for you of finding him in this picture, and there he is. That's you. Yes, it is Jingquan. After his graduation from East China Normal University, he moved on to do his master's at Guangzhou Institute of Chemistry, which is a division of the Chinese Academy of Sciences. And there, he specialized on terpene chemistry and heterogeneous catalysis, and one of his main discoveries was the conversion of myrcene to myrcenol, a very simple-looking transformation, but bewilderingly difficult to actually execute. And it's quite profound, actually, because probably everyone in this room has used myrcenol today, or you might have eaten it as well. It's produced about 100 or 300 metric tons per year, $100 million a year. It's made by this company in China, and not surprisingly, they use the procedure that Jingquan developed as an undergraduate. And it is, in fact, still a trade secret. If you visit other companies, they still don't know how EcoGreen does it. Well, the Chinese Academy of Sciences licensed out this procedure to EcoGreen, and they made so much money that the president of China himself authorized a full scholarship for Jingquan to go to Cambridge. And so the next trek in his journey was to go to Cambridge University, where he worked with Professor Jonathan Spencer on a whole variety of topics, ranging from biosynthesis to physical organic chemistry. Here's a picture from back in the Cambridge days. He was promoted to a junior research fellow at Cambridge before his PhD. He then did a postdoc in 2001 with E.J. Corey, and during that time, he studied Lilic CH activation, developing a procedure that's been used multiple times in academic settings, but also in industrial ones. So this recent paper from Merck, they used his procedure, and they specifically comment that the only way they could do it was using Jingquan's procedure. He moved to his independent position in 2003 at Cambridge University. Shortly thereafter, he was lured to the United States, worked at Brandeis for a short period until we were able to convince him to come to Scripps in 2007. Shortly thereafter, he received tenure as a full professor in 2010. And if one had to encapsulate his research in just one statement, I would say it is practical, real-world CH activation. That is, CH activation had been out there for decades, but it hadn't actually been useful, something people had thought of actually employing in synthesis. And for those of you who are biologists or maybe not associated with his research, let me just mention that the parallel here in chemistry is to the Panama Canal and shipping, where the union of the Atlantic and the Pacific sort of changed the whole world. And in the same way, the way Jingquan does chemistry has changed the way we look at a CH bond and made things a lot more simple. If you want hardcore metrics, there's a lot of citations. His rise to fame has been meteoric, and it's pretty incredible. If you look at that last 20 papers or so he's published, have 100 citations. The authoritative review he wrote a couple of years ago has now garnered about 600 citations. In chemistry, that's pretty good. He's won a number of awards, probably all the ones that you can win at his stage of the game. And so you're probably all wondering, we even have administrative members here that are probably wondering, what exactly is this H-index? This is rather controversial, right? Because some people don't like H-index. And it all depends on which H you mean. If we're talking about his health index, I would argue that Jingquan has got a very impressive health index. He was a champion of his badminton club at St. John's College in Cambridge 2 years, 2001 and 2003. And here at Scripps, he is actually quite renowned for his weightlifting talents. He's set new records. He's 2 times his body weight currently, but truly impressive, not only in the lab, but also at the gym. Another one which is quite, I think, important to keep in mind is that other H index that we often forget, which is the heart index. All of us who know Jin-Kwon well and all of the colleagues can agree unanimously and vigorously that he is the most beloved friend and trusted colleague to all of us. So thank you, Jin-Kwon, for everything you've done for us over the years. It's wonderful to have you. It's a gift every day to have you here. But I think the most important H index is not the 2 I mentioned, or even the one that Thomson Reuters likes to advocate, but rather the hair index. From Newton to Franklin to Einstein and yes, even Pitt, it has been a sign of affluence and strength and great health and scholarship. And when Jin-Kwon started here in 2007, his H index was very poor. I don't know why we hired him in retrospect with that kind of low H index. And then it got a little bit better in 2011. And then recently it's just been completely off the charts. And, you know, I have to say, before I turn the floor over to you, Jin-Kwon, they often say that imitation is really the greatest form of flattery. So it's with my great admiration that I turn over the floor to our beloved colleague, Jin-Kwon Yu, for the faculty lecture.
Thank you so much, Phil. I kind of noticed that he was very busy today, and now I realize actually Phil is giving the main lecture, and I'm just helping to wrapping up, really. But anyway, thank you so much for that very creative introduction. And certainly I want particularly to thank on behalf of the audience for all the entertainment, but at my expenses. And as Phil has said, we have been interested, in general, CH activation, the field of very gigantic field really for now almost 10 years. And there are still so many challenges, and that's the good part, about this area. But let me point out very simply before I even start to talk about, before I even introduce you anything, that is the single important challenge, most significant and important challenge in this field still, is how do we discover new strategies, and more specifically maybe a privileged or even almost magic ligand that can accelerate CH activation reactions by precisely lowering the transition state of the CH cleavage step. Only once we have that power in hand, we can then really start to dream about enantiomer selectivity, regional selectivity, and today I will even show you site selectivity. Once we have those, then we can broaden subject scope and eventually provide a shortcut, but a broader shortcut to molecular complexity from truly chemical feedstock. And hopefully you will see some of that is really coming in our laboratory. But before I move on to tell you a couple of stories, I do want to provide or share with you some of our perspective. It turns out to be very simple but very important as a guidance for what we should be thinking about when we're working in this area. That is, CH activation is a huge area, and it's very important we realize to divide this huge field into 2 subdivisions, in my opinion. Not like a soccer game. It's not a premier game here and second division. They are equally important, but it's very important to separate them. The first one is, we call this first functionalization. That is, the best example, of course, is the methane to methanol. But in my opinion, from synthetic perspective, the winner or the very competitive approach is going to be enzymatic transformation, especially biodegradation from straw and from raw materials. I think it's going to be hugely competitive and through evolution of enzymology. And I'm not going to predict, but that's how we feel about it once we've been in this field for a while. However, once we reach this 100 or perhaps even a couple thousand, but still far away from being enough for medicinal chemistry, for biological system, for natural product synthesis, is to ask a question. How do we take this $1 kilo, $1 sustainable chemical feedstock and move up the complexity very rapidly to reach medicine, agrochemical, electrical devices, polymer materials? And I can show you that so far we have made impact in all this area. Our chemistry has been used, actually. So the question is very simple. When you start to move up the complexity, the constant question you have to ask is, how do you buy the complexity at minimum cost, minimum step, minimum time, and as well as minimum waste? And that's very important as a sustainable synthesis into the future. And if you can think about drawing a picture from a relatively, basically a plain sheet of paper, what you need is each stroke you make, or brush you make, you have to be ideal choices. And therefore, the choices here turns out to be the crucial. And that is actually a luxury for CHI aviation field. What does that mean is you want to be able to precisely install almost any function group you want at a particular position and at each a particular step. And there are many approaches towards CHI aviation, and based on what I have said, we have firmly made the decision, very firm decision, that is, we must focus on developing new strategy to insert a metal into the CH bond. Why? Because once you have the carbon-metal bond, particularly magic carbon-palladium or carbon-carbon bond, based on known knowledge, we pretty much, there's a possibility we can turn that carbon-metal bond into a long wish list of function group, or even carbon fragment, or even polymer through that kind of chemistry. And that's what we really want to do. So here is the dream list, as I mentioned. I remember Phil mentioned that when I was interviewed here, every of my great colleagues asked me here, what do you want to do? And I told them this is what I want to do, but I was very lucky and relieved that nobody asked me, how are you going to do it? And if they would ask me that, I would say, I have no idea, basically. But let me tell you the truth. So far, we have published all those transformations, except these two blue ones are still very tough. But we thought this is never going to happen. But 2 months ago, we published the first rare example of sp3, sp2 CH boronation by palladium catalyst. Yesterday, one of my very best first-year student, Jen, told me he has made this happen. And actually, in the extraordinary fashion, surprising manner, highly effective. We can put an alkyne onto the CH bond, and you can imagine that it can connect to Scripps click chemistry, and that will give you a new dimension, for many, many possible applications. So, why we chose the choice and diversity? There are many examples I can give you to convince you, but this is my favorite example. As I mentioned, we really would like to push natural product synthesis and drug discovery all the way back to chemical feedstock. And pivatic acid is a good one because it's cheap, readily available, but it's a very interesting structure, quaternary carbon center, very expensive to have. And yet, this is a dead end for any synthesis because all the 3 dimension really is totally blocked. You're going nowhere. It's like a French cul-de-sac, right? You're going nowhere, one direction, but you can't go anywhere. It's frustrating. However, if somehow you can magically break one of the CH bond, immediately you hit the drug molecule. And indeed, this is a Pfizer drug molecule, but Glaxo Wellcome has used our recent technology, built up a huge library, and 3 candidates has been found, a very powerful candidate, by just one step, minimum library, making a drug discovery library. But of course, that's a good example, but it's not broadly applicable to anyone, everyone. So what we then needed to do is perform an enantiomer selective CH aviation, set up this chiral center, then followed by a very unusual olefination perhaps, because then we connect to Barry Sharper's chemistry here, introduce further chiral center. And if you compare this molecule to the pivatic acid, they don't look like brothers or sisters. It's hardly possible to recognize it's come from there, right? But if you do a simple math, if we have the choices, 100, 100, and 100, you can imagine almost any quaternary carbon center you can make. And in my opinion, in the drug discovery, we have been doing very well making flat molecule, which is great. But on the other hand, if we just focus on that, that certainly will create enormous redundancy in terms of new chemical space. And really, it's time to look into a different dimension. But it's hard. It's not easy to make 3 quaternary carbon centers, tertiary center, in the level of efficiency like Suzuki coupling. We can make them, but not as good as Suzuki coupling. And this, I believe, is some of the possibility we can potentially do. Having all those in mind in terms of broader picture, then immediately you have to plan carefully what kind of catalysis you have to develop to actually make this happen, right? So if you look into literature back then, 2002, when we started out in Cambridge, this is something that's reasonable to look into, is the palladium-02 catalysis, invented in 1980s, actually, right, the concept. And the catalysis is very simple. It's identical to Heck reaction. You take a palladium-0 phosphine, you do oxidative addition, and if you treat the double bond here as a double bond, and then basically it's Heck reaction. And indeed, even the mechanism goes through the same way as a Heck reaction, right? Although we call it CH activation in many cases. But the big problem, as you can tell, this chemistry is limited to bi-aero forming product, right? And immediately that doesn't fit what we wanted. As remember, we want the choices. Enormous choices. Whatever you want to put in, we want to put in. That's the important part. But this has changed a little bit. 2 years ago, one of my students, a wonderful student again, Masawaza, was able to break this lock. and show that this catalysis can be used to functionalize sp3-CH bond in thermodynamic fashion. And this certainly changes the gear, changes the perspective of this catalysis, because this cannot go through the same reaction mechanism because you don't have a double bond at all. And the CH radiation actually was the first time convincingly showed this can happen. But so far, if you look into the last 3 years, only one example, still this is the first example and only example, that tells you something, that this chemistry is tough going. It's not great. But as I already hinted, that Jen, the first year student, was able to show this may have a future. But so far, we are still the only group to really do this chemistry. That's not necessarily the great stage yet, big time yet. Another catalysis that has perhaps caught most of the attention in, I would say, from 2002 to 2008, and that is the 2-to-4 catalysis. The concept or the crystal structure or whatever the catalysis was established first by Canty and then demonstrated beautifully by Epperson and then Tremont and Stock, acetoxylation, CC bond forming in 1970s, 1980s. And then, of course, the younger generation, Sanford in Michigan and myself in Brandeis at that time, started out to exploit this catalysis. And clearly, we will not try to reinvent the catalysis. The idea is, can we develop truly broadly useful synthetic transformations by using this catalysis? And let me just keep it very brief. In summary, so far, we have discovered far more problems than solutions. And that is not necessarily bad for science, of course, but that's the state of art. And what are the biggest problem, in my opinion? Number one, we still cannot use truly practical, economically efficient, oxidant, namely air, because you just can't do that catalysis through this kind of idea. Secondly, perhaps even more difficult, is if you oxidize the palladium-2 intermediate to palladium-4, as you can see, you have too many fragment choices that will be cis to the aromatic substrate. That would do reductive elimination. So basically, you will get a mixture of compound product, and that is a disaster for ton scale. That is my aim. My aim is to really eventually to be able to produce ton scale drug molecules using this chemistry, and this is not going to happen if we can't solve that problem. So we came up with the idea using fluorine fluorine as a bystanding oxidant. What does that mean is if you use a fluorine, you could generate palladium-4, forming a palladium-fluorine bond, which is bad if you want to do fluorination, but it's good if you want to avoid that reductive elimination. That will give you selective product, right? And that's what we did. But again, fluorine is not a practical oxidant, but it's a good concept. So far, it has been caught up by many, many groups for gold catalysis and CC bond cross-coupling, but it's not the future of this area, in my opinion. What really I want to focus today, because the redox chemistry can be very complicated, to keep it very simple, let's just focus today on this brutally simple catalysis, 2-to-0. That is, by activating the CH bond first using palladium-2, then you can react with any nucleophile, ideally Suzuki cross-coupling nucleophile, to form a CC bond, a CO bond, CIOD bond, or whatever bond you want to make. And that is the very simple catalysis. But the beauty is, number one, the palladium-0 can be potentially reoxidized back by just air. As you know, CH aviation in principle is uphill catalysis. You have to borrow energy from somewhere, and you might as well just borrow from air. It's the cheapest one and the easiest one. Number two is, for the first time, I believe, we have made a broadband connection between the esoteric CH bond activation as a very esoteric language to a broadly speaking language, Suzuki coupling. And therefore, it's quite obvious, self-explanatory, why this catalysis could be broadly useful. Basically, you can do Suzuki coupling, right, this catalysis. We just needed to do better. Once we have the catalysis, then another very important challenge clearly came to the table, that is the reactivity and scope is a huge problem. Why? Because in the last 50 years, basically 99% of the paper focusing on CH aviation using strong coordination. We always believe the substrate has to strongly coordinate to the metal so that you can have some proximity. Then you can do the CH aviation, which is a very good idea, of course. But the problem is that it would require certain specific structure of the substrate. But a fundamental problem is if you look at the reaction coordinate, if you use strong coordination to promote the CH aviation, right? The transition state is good because you very well organize the transition state. But then you drop to the sink, the thermodynamic sink, through this BIS coordination, strong coordinating group, then it's very hard to do catalysis, to climb out of the second mountain valley. And that turns out to be a huge problem for everyone if you want to achieve high turnover frequency, broader scope, reaction, and subject scope. However, if somehow you can just push this up a little bit using a weak coordination, you can imagine solving that problem. But the psychological problem is everyone believes the CH aviation needs strong coordination. And indeed, that turns out weak coordination is not a problem at all. It's only a psychological problem. It turns out to be great for CH activation, and therefore that has been a major breakthrough from our laboratory, the weak coordination as a very powerful tool to promote CH activation and the catalysis. And I have to say, the big bonus coming from this belief or this hypothesis is once you're using substrate as a weak coordinating reagent, then you can think about using ligand as a competitive coordination to influence the transition state. Think about it. If your substrate is a very strong coordinating, that leaves you very little room to really influence the transition state, electronic and sterically. So it's very important that you work with weak coordination. Then you can have a ligand to come in to tell the catalyst where to go and what to do, steric selectivity, regional selectivity, or even site selectivity, and you will see that, right? Okay, so here is the first part of my talk, if you're still awake, okay? The first part of the talk is what kind of catalysis, and this is very simple, as I said. We want to do Suzuki coupling, basically, but using CH bond. I don't think you should call that as a Suzuki coupling because it's completely different in terms of reactivity, redox chemistry. And on the paper, it looks great. You cleave the CH bond, say we can do that. Now you can almost do similar thing like a Suzuki coupling, couple with a nucleophile, organoboron, to make the CC bond. You drop the palladium 0 out, reoxidize them back to close the catalytic cycle. But if you look at the catalytic cycle, you know it's impossible because the palladium 2 will not cleave the CH bond before they react with the more reactive organometallic reagent in one part. You can't even do stoichiometric. If you mix them in one part, all you get is palladium black. And that's indeed, Xiao Chen and a couple of other postdoc students was practicing just recycle palladium black in the first 3 years. And there was nothing you can get, okay? But let me tell you, particularly to the student, the most important lesson we have learned is with this kind of project, it's very difficult, important to convince yourself to just really insist upon it because many students would just run away if they figure out this is not possible, and some students, if they don't know that, they go into the middle of a few years, then they run away, and that's even worse. But you really needed to stick to the end, okay? And Xiao Chen was the only one who stick to the end and finished this catalysis. And let me just show you how this works. You can take this substrate, aromatic ring, cross-couple almost like a magically to tin reagent or organoboron reagent, right? And this looks really great in terms of catalysis. But in terms of synthetic application, this is going nowhere because it's almost like you're building a house, but you're building next door to the volcano, and nobody's going to rent this, right? Because it's not useful. It's very impractical, and you have to install a direct link group, and it's very strong coordinating, so the catalysis is not very fast either. So clearly, we needed to look for new reactivity and new scope and using weak coordination. But if you think about practical side, what kind of substrate actually we should begin to start to think about? You don't need to travel very far from Scripps to look for the inspiration, right? If you look at hydrogenation and Sharpless epoxidation, the writing is on the wall. What we needed to do in the area of CH aviation is we have to meet the following 2 criteria. That is, the substrate are readily available in both quantity, 1 kilo, $1, and also diversity. Wide range of substitution pattern can be bought cheaply from Aldrich. And the second, the product can be mapped into a structural motif very easily. For instance, in this case, it's amino acid. That will go on to peptide, right? Everybody would be interested. And this one will go to polyphenol, polyhydroxylate compound. That can be carbohydrate or polyketide. So that is the 2 criteria you have to think about. What kind of substrate you really want to work on. With those in mind, then it's very simple to give a dream list of substrate. Benzoic acid, you can buy hundreds of them from Aldrich, very cheap. Amine, if you want a heterocycle, or alcohol, or aliphatic acid. All of those are very cheap and readily available in diversity. But to add another dimension of flexibility, what is very important is the distance. That is, can you also have some flexibility between the CH bond, the distance between the CH bond and the function group? Because then you can start to plan different carbon skeleton. For instance, this one you can make lactone, and this one you can make indolene. This will be quinoline, right? It's different. Everything is different, but it's the flexibility that really matters, will hugely impact when you make a molecule, okay? And let me then show you one example, natural product synthesis, and I think it's the most appropriate in front of some of the very best synthetic chemists in the world, how our chemistry eventually can impact our synthesis. Unfortunately, we are very lousy in terms of planning synthesis in my group, but what I would do is just to show you to chop this molecule into pieces, and I would say we can make each pieces through CH aviation. And then if we still cannot make the molecule, I can only blame Phil Barron for not helping me. If only he could spend 5 minutes with me helping me, I think we would have finished this molecule. But he was too busy with his own molecule. But let me show you how we do this. So you take the brew pot, we can take, again, malonate acid, right, feedstock chemical, enantioselective CH cross-coupling, set up this chiral center. If you take the middle core structure, benzoic acid, we develop the hydroxylation chemistry to install like enzyme, hydroxylation here. And that will give you huge versatility in terms of plan when to install the hydroxyl. You can also install the hydroxyl at the late stage, or in the middle, early, or even in the last step. And that gives you a lot of flexibility. And of course, the green part, we can actually take the benzyl alcohol, recently we published, to direct CH derivation, and then couple with heptene, again, feedstock chemical. We can one step cyclize to make this green structure. So what's left is, how do we utilize the synthetic wisdom and develop a new strategy to fit this method, and eventually we can finish this molecule. But that's just one example. Of course, you will see, actually, we do finish natural product. In a moment, you will see that. But let me then, at this point, turn the clock all the way back to 2002 when I had one student, when we started to enter this area. What happened? What happened was the first approach we decided to, using a chiral auxiliary approach to develop CH derivation. But let me tell you the truth. We were not really interested in developing chiral auxiliary for CH derivation. What we were really interested is to introduce, for the first time, in a very defined way, using stereochemistry as a physical organic tool to really peek into the inside of a transition state of how CH derivation could happen. Although the referee didn't seem to appreciate that, this paper was rejected for 1 year in 2004. We couldn't publish anywhere until Peter Gerlis came to rescue us, and it was great. It did see the light in the end. But the beautiful lesson we have learned can all be shown by this crystal structure. In the end, we actually established this structure by NMR study, like a protein structure. We did a lot of solution NOE study, 2-dimension, and NMR study, and we reported, proposed this structure. But 6 years later, we were able to get this crystal structure to confirm the hypothesis that people thought it was impossible 6 years ago. But what does this teach us? If you do one-step retrosynthetic analysis, the most important lesson we learned is before the CH derivation happens, the conformation is far more important than the strength of the coordination. You can perturb the coordination strength by introducing sterics. You can also control the conformation and see the correlation. It turns out the key for the reactivity is the CH bond here has to be roughly coplanar with the palladium acetate bond in the square planar structure. In terms of dihedral angle, ideally you want to be within 10 to 20 degrees. If that can be met, then this CH derivation is unstoppable. You can have this in 0 degree. You can lock this guy up in the fridge. The CH derivation will still go forward. And that is very shocking at that point. For the first time, we see that 0 degree sp3 CH derivation can happen catalytically, right? But what is the big question at that point is, instead of be happy with this, is to ask the next question. How can we then develop this chemistry with a real world CH derivation, as Phil Barron just said? And that means, how do we mimic the structure, but with real substrate, benzoic acid or aliphatic acid? And you know that's impossible, because this is how you would see in the solution structure. Or this one, that's what you can see also, but in a small quantity. And the palladium oxygen bond, of course, single bond is free to rotate. And that will lose all the entropic gain if you want to pre-assemble the pre-transition state. That is a problem. And then a very interesting crystal structure deposited in Cambridge database really came to rescue us. That is, the sodium cation, it was shown to beautifully coordinate to carboxylate in this structure. And there was one structure in the database. So then what we thought is, can we use the sodium as an auxiliary, but reversible, like a non-covalent, almost like Carl's organocatalysis, right? Reversible, non-covalent kind of auxiliary. Can we then use palladium to grab the lone pair to do the CH derivation? Then the question is this lone pair really nucleophilic or not? It turns out in 1980s, Tony Kirby from Cambridge and Ken Hawk in UCLA has done beautiful work to calculate the E lone pair, the energy-wise. I have no idea why they're doing that, but it was a beautiful study, fundamental study. But for us, it was very reassuring that this might have a chance. So we then came up with this idea. We need to find a magic student who's willing to stay on this project for 3 years without publishing anything, and that is very hard. And in the end, Tyson was able to show us the following result. By mixing the substrate with palladium acetate, you can even take one equivalent, stoichiometric. You can hit this from 50 degree to 150 degree. Nothing is going to happen except decarboxylation, decomposition. Okay. However, if you just walk to the kitchen and just get 1 spoon table salt that you would use for French fries, quantitative yield of CH derivation would happen. And this is quite shocking, right? Because for the first time, physically, we confirm the weak coordination indeed can direct metal insertion. I don't think there's any other example like this, firmly proven that you don't need much to really do the CH radiation. And you might ask, why it took us 3 years to discover this? It turns out this complex it looks like it's just a palladium black. We form a very nice thin film like palladium black on the glass wall, and we have washed down to the sink for many, many years probably. And that is a very good lesson. But the real lesson is, you can do screening, it's very important, but I think it's far more important you are working on hypothesis-driven research. Because without that hypothesis, we would have given up a long time ago. Because we believe this hypothesis, we just believe this got to work, and eventually we just get it to work, basically. So the hypothesis, disprove or prove the hypothesis is always fundamentally very important for research. Now I'll cut a very long story short. It's all magic. We can somehow take this intermediate and do all kinds of transformation, and this is a very small fraction. Basically, all works. And you probably haven't seen the fluorination, trifluoromethylation yet, but that will come out next 2 weeks. We have done that. So in boronation, I said, is coming out, and the L-carnation will add it to the list. So it really works really well, okay. And what is also surprising is, by using this weak coordination, then in combination with a ligand that I have to jump ahead a little bit, you will see the ligand, but now I'm not ready to talk about the ligand. This kind of substrate also works. Not only carboxylic acid, ketone, even remote ketone, hydroxyl, even ether, okay? But all those are inspired by this chemistry. They are the same concept. It's the weak coordination does take you further in terms of CH radiation and catalysis, okay? So that is the first part of our talk, really, but let me just show you, is this useful? And indeed, a group from Japan has finished the kanamycin using our latest stage hydroxylation. Professor Andy Miles had made a huge difference to his project. He just finished this. He's going to scale this to kilo, but now he's made a 20 gram of many, many analogs using our chemistry, hydroxylation chemistry, using just air and our catalyst. So that is very encouraging. And from Europe, I just select from different, geography. Actually, there are many more. And this is from Fershner group. They have used our chemistry, again, in a later stage, 10-gram scale, using our chemistry, made this natural product. So it's clearly very easy to use for synthetic chemistry now already. But a fundamental challenge, another very closely related fundamental challenge still is sp3 CH elevation. It's pretty hard. And it turns out this table salt idea doesn't work with pivatic acid. Got us 38% yield the first try, and that's very encouraging. And we didn't have to do too much to get a better result. That is to play a little trick to protect the carboxylic acid in the form of Derek Barton's group. We call this musket ester, right, for protecting group. If Phil, you don't like protecting group, but this is very easy to use, okay? This is Derek Barton invention for ester protection. So indeed, the yield immediately goes up, and the fundamental concept you will see immediately why we think this should work. They behave exactly the same as carboxylic acid, except the known pair, the Lewis specificity of the known pair, just increased a little bit. So they grab the palladium a little bit faster, a little bit better, and that gives you the extra 30% yield. And this is what I said. Glaxo Wellcome is building a platform for drug discovery using this one reaction, basically. And again, the huge test is, can we do diverse transformation with sp3? Indeed. We can do Suzuki coupling. We have a comprehensive paper coming. Just collect every Suzuki coupling partner, double bond, Heck reaction, alkyl, or even carbon monoxide, right? And you can see this is the advantage of a weak coordination. You basically can do amazing transformation. Even you want to do a halogenation here, do a Heck. You cannot do this sp3 Heck reaction anyway. It's just hard to do. But now you can do that. And as I said, when we put forward the table salts idea, we certainly received many, many doubts and criticism. But 2 weeks ago, thanks to a wonderful student, Xin Guo, was able to finally get another crystal structure to show the amide works exactly the same idea. The cesium is coordinated to the oxygen, and we form this kind of imine. And imagine if you have carboxylic acid, they will behave the same. The same idea works in different cases, but the crystal structure shows clearly. And honestly, we had a huge problem in convincing people before we got the crystal structure, but now we have the crystal structure. And just give you a little hint how we can apply this chemistry to broader range of asymmetric catalysis. You can simply take the 1 kilo, $1. Many of those will be made 1 kilo, $1 very soon because of the rapid development of enzymatic catalysis for this kind of molecule. The key is, can we use our chemistry to build up a new library, new skeleton, through just one-step transformation. But again, the key is the choices, because you want to make whatever you want. So that way it will give you the true flexibility. Let me give you one example. If we have, Eric Carrella actually have reported the best example probably, using this molecule to make polyketa. but he has to plan the synthesis so carefully so that the alpha methyl will end up at the right position, at the right step, in the final step, basically. But now, with this kind of ability, you can really worry much less. You can just design your synthesis in a completely different way. Okay, so with that, I hope to convince you that the catalysis is working. And the subject scope is also very promising, but I haven't shown you the best scope yet. But at this point, I want to show you how we then develop a ligand to match the weak coordination and really have a control in terms of regional selectivity and rate and catalysis. And here is the first example. As a biosynthetic chemist, that the first thing you learn is the assay, right? The assay is the most important. And the CH derivation is the same. You don't have a good assay in the CH derivation in terms of ligand screening. You see many, many papers might have some ligand, but the ligand has nothing to do with the transition state. That's the problem. So we set up this assay to look for the 95% E above, and with that, we can have some confidence. Maybe the ligand is involved in the transition state, maybe, but it's good enough, right? So we set up this reaction to really look for the ligands, and let me just tell you what the potential pitfalls might be if you're in this field. The first problem is the two subjects could coordinate to the palladium, and if you have a strong coordination subject, that could be a problem. You would have no inference from the ligand. If the two ligands is too happy with the palladium, then you have no reactivity. That's another big problem. How do you displace the ligand by weak coordinating substrate? That's another tremendous challenge, right? And basically, what you really want is you want the ligand somehow really likes the substrate, so they can dance together whole night without exchanging the dancing partner. And that is not trivial because the catalytic cycle, each step you can go wrong. And you really have to make sure they just dance with each other without exchanging. It has to be high fidelity. And that's not easy to achieve in uphill catalysis, right? Okay, but we failed totally by trying to achieve that through NMR study, quick-struct study. We can't find any ligand that's available out there from Aldrich or from anywhere that would do that, okay? So we decided to take a turn, totally adopt a different approach. It's based on this quick structure that we obtained, the acetate. We decided to play a game with the palladium acetate by replacing the palladium acetate with carboxylate or chiral carboxylate or chiral phosphate. We hope when the CH derivation happens, that chiral center in this alkyl chain might influence the transition state to set up the chiral center. That was the basic idea. And surprisingly, we were able to get actually 20% EE for a couple of years and didn't move up. So we thought perhaps the palladium oxygen single bond, this is a single bond, not an add 2, it's add 1. Maybe it's free to rotate, and that would really erode the chiral information that you try to relay to the substrate. So what did we thought? What we needed to do is to fix the conformation by introducing cyclopropane rigid conformation. That might help. Indeed, the EE bumped up to 45, and that was a big celebration because it looks like we really smelled it. It might be happening. So we then decided immediately to look into the detail of the structure and EE enantioselectivity relationship. As you can see, if you change the alpha chiral center from S to R, you get opposite chiral induction. But if you change the beta position from R to S, you get no change. So that's kind of very confusing. The molecule certainly is trying to teach us something, but we were not smart enough to figure out at that point. So we remembered Kagan had this famous C2 theory for asymmetric catalysis. So we decided really to, at this point, we need to make C2 symmetric ligand, pseudo C2 ligand. That would take 12-step synthesis, and we need 20 gram. And Nathan has been working on this for 3 years, and he was very tired. And he said, there's no way I'm going to work on that. It's not going to work. So fortunately, a new student just arrived. I was able to persuade him to take on this project, and he made it. And it turns out Nathan was very smart. It was absolutely zero EE, this ligand, okay? But let me tell the student, this is the best breakthrough, in my opinion, in the field. Because this tells you precisely that give us a new direction, why this thinking was wrong, really guided us to look at a different direction, to rationalize this result. So what we did is to remove everything, keep it as simple as possible. That's always the way to go. When you get confused, is to simplify the system, just like you do biology, right? So this is what we did. We keep only the ligand, palladium, and substrate, nothing else. And we started to study extensively NMR structure under various temperature conditions, and eventually, through inorganic synthesis, we were able to actually synthesize this structure through a very complex inorganic synthesis, multiple steps. Once we look at this structure, then we realize what's happening here. This molecule basically did a very clever way to self-assemble this structure that you could never imagine to have. First of all, this ligand is very loyal to the substrate. They always coordinate one-to-one through the steric effect, through the trans effect, and you would always have one-to-one. The second ligand cannot even come in. They would just repulse each other. And the substrate cannot compete with the ligand, of course, because it's bisdentate. So that, by doing that, the bisdentate anion and sigma donor weak coordination, we set up this structure. And then if you look at the stereochemistry, it's even better. The alpha chiral center come from the nature, which is very cheap for further development, right? You don't need to worry about the chiral center, chiral source. And that isobutyl group is very aggressive, like a basketball player, like LeBron. They start to elbow the bulk down. You push the bulk down, and the bulk gets very upset, very unhappy. They start to push the substrate, the bulky part, up, and that will set up the stereocenter. This is not a transition state, but in a moment, actually, I may not have time to show you the transition state, but this is roughly how it works, okay? So now, let me tell you how lucky we were. If all that worked out, it would be great, but you can imagine, if the pyridine doesn't listen, if they coordinate from the front, we would be totally in trouble. That would give you absolutely R and S 1-to-1 ratio. But we lock it out. This ligand dictates any sigma donor has to come from the trans, and that by computation study was proven. So the trans effect, we were very lucky that substrate would come from the behind in a very exclusive manner. And I have to confess, we have never designed such a plan, but it just worked out. But I have to give all the credit to the student for working on this for so many years, and eventually came up with this beautiful monster, controls everything, basically. We call this smallest enzyme, almost like a protein, right? Small enzyme. And once we have that idea, we then just modify this protecting group, because we knew from the serum model, all we need to do is to keep modifying the protecting group. As you can see, 95% E, exactly what we wanted. We were convinced this ligand is involved in the transition state for the first time catalytically through uphill catalysis, right? And indeed, can we do the table salt trick? Indeed. This weak coordination matches this ligand as well, because it's a very special weak coordinated ligand, and that gives us 97% E. And of course, the next challenge in this direction is to push forward for aliphatic acid, aliphatic amine, aliphatic alcohol, so on and so forth. And that's all up and coming. And actually, thanks to Phil sending one of his best students to me, and he's getting 80% EE in this direction. Very exciting, just 2 weeks ago. Okay, but let me tell you what we can already do. In collaboration with BMS on a project, they were very interested in a new way to make cyclopropane-based biologically interesting medicine molecules, right? And basically, usually what you do synthetically is disconnect here and make it a double bond, and then you do carbene, or many other ways you can do that. But now, what we are saying is buy 1 kilo, $1 substrate again. One substrate can give you thousands of analogs by just doing cross-coupling, set up both chiral center in one step. Okay, and if we can handle alpha hydrogen here, that would be even great. Then we can rationalize through thermodynamics. We can get trans as well, chiral center as well. So that would be very versatile way to make diversified chiral cyclopropane molecules. Just one example. But I think the fundamental question still remains to be answered. That is, did this ligand really push up here through acceleration of the CH derivation step, or did it decelerate one of the pathways to achieve the enantiomer selectivity? That's not clear. So to do that, the first thing we did was to select all those substrates that's known to be not reactive at all. No one can do any CH derivation with this kind of substrate. Not only because it's electron deficient, but also it's too far away, the function group. But if you just add the ligand, it's almost magic. The reaction starts to work. So that's very encouraging. Tells you the ligand is doing something really significant. It's accelerating primes. And of course, what you need is Donna's expertise here. We set up this kinetic experiment very beautifully. You can show, and I don't want to show the detailed kinetic data unless Donna is prepared to answer the question, okay? It's very confusing, all the data. But the bottom line is it works, okay? It is accelerating the CH activation step. And that is also confirmed by computational study recently as well in another JAX paper, independent JAX paper. So, but let me just also give you a little slight different information. That is a physical-organic classic. It's always my favorite physical-organic kind of perspective. So far, all the palladium catalyzed CH derivation would always work better with the electron-rich substrate, and it would not work very well with electron-deficient substrate. But with this ligand, you can see this one is faster. That tells you clearly this ligand has switched completely, the ligand, the paradigm. We're not working with the Fujiwara type of Friedel-Crafts reaction anymore. We are into a new paradigm of CH cleavage through the new ligand to accelerate CH derivation. And that is very important because, as I said in the very beginning, only if you can achieve the acceleration, then you can have control. And indeed, once we have that, we can have high turnover. This one, 500 turnover, and according to Pfizer, we need to bump this up to 1,000, then we can be in ton scale for drug production. But at the moment, this is a world record for this kind of a real substrate in one equivalent. 0.2 mole %, 20 minutes. Pretty much you can basically stir this reaction in beer bottle, and 20 minutes later you collect all the product. And if you compare this to Heck reaction, in terms of practicality, what do we have here? We have almost nothing. We have the ligand catalyst, potassium bicarbonate. You would need that for HEC, and we just need air. We don't need nitrogen, that's all. It's very simple conditions, right? And Kiri Ingo, of course, now is visiting Oxford as a SCAC's Oxford program. He really was responsible for discovering this new ligand scaffold, and he's a great marathon runner in Los Angeles area, but he admitted he can never beat this timing, 20 minutes. It's going to be very difficult. It's a very fast reaction, right? And of course, synthetic application, just briefly, as I said, the key is, can the product be mapped onto a wider range of representative structural material in synthesis? And indeed, tetranone, naphthalinic acid, all these are made in 20-gram scale. Okay, just to show how powerful this method is. 2-step, otherwise 8, 10-step to make this structure. But we can make this, publishing science paper makes this in 3-step, very fast synthesis for this complex structure. And of course, it's very important to demonstrate this ligand is compatible, not just for olefination. Can we do many other reactions? Yes, Suzuki coupling reaction without the ligand doesn't work at all. With the ligand, it works really well, but we need a better ligand perhaps. And also works with alcohol, not just carboxylic acid. At the moment, Kevin, another second-year student, has discovered you can do amine. So we can do carboxylic acid, alcohol, and amine. All of that need this magic ligand. Without the ligand, it would not work. So that's very important. And of course, there are many other groups are beginning to using this ligand from Chicago, from Spain, and this is just one example for modified estron, again, medicinally relevant molecule, late stage modification using our chemistry. And in the end of the day, of course, particularly to this audience, I just would like to share with you one of the synthetic project we did, and it's very modest in terms of complexity, but I want to show you how this could potentially change the way we think about in certain structural motifs, right? And if you allow me to, if I may ask you to forget about the first 6, 7 steps, because according to Phil Barron, this can be cut to 3 steps, but we didn't have time. We just made it, made it 7 steps. It's awkward. But what I really want to emphasize is once you reach the late stage, can we put the 2 pieces together to make the final product? That is the challenge, right? Because if you want to do Hecker reaction, to install the bromine here, that's almost impossible. And if even you have that bromine, you made it by 7, 8 step, make the bromination here, you still cannot do the Heck coupling because this alpha hydrogen is extremely sensitive. They would just decompose at many conditions. But this is a very mild condition, 85, almost a neutral condition with the ligand, 93% yield in the last but second step. That tells you this chemistry is compatible for synthesis. But the point I really want to make is once you have this kind of unusual, unprecedented disconnection, that opens a new door to think about synthesis. Let me just show you what do I mean. So let's make this key disconnection. On the right-hand side, there's a benzoylfuran structure, very representative. On the left-hand side, basically you can get this ingredient from your backyard if you cook Indian food. This is a very simple, spicy basic component, very cheap. So the question is, how do we then construct this molecule? We decided to go for another situation. So we developed the hydroxylation, 1 step, make this one. Once we reach here, then that gives us another opportunity within the NSF Center. We collaborated with Hugh Davis by taking cabine and this benzyl alcohol, 1 step, set up all the color center. So we call this 1, 2, 3 synthesis. Taking all those molecules readily available, 1, 2, 3, only CH radiation. We made 20 analog of this natural product. I know the industry is giving up on natural product for medicinal discovery, but I think there's a lot of coming back. If we can make a natural product within 10 steps, why not? Because they are beautiful structure to be exploited. The key is, can we make many analogs just like medicinal chemistry? Has to be within 10 steps. In this case, 4 steps. We still have to deprotect this methyl ester. That would be 4 steps to make this natural product, right? And that's the point I guess what I want to make. So let me then summarize fundamentally what we can do. We can basically, in terms of direct CH derivation, we can pretty much do all of that. Benzoic acid, ketone, the ketone will be submitted soon, alcohol, ether even, we can do that. It's great. And those chemistry are just as important as many other non-directed CH derivation. But in principle, we still would like to do others, meta and para. And in the interest of timing, I don't want to tell you all the example. Let me just tell you one example. How do we approach the meta-selective CH derivation? So what we decided to do is to listen, speak and listen to the electronic property of a substrate, and then design a ligand to match that, see whether we can control the metal selectivity without going to the ortho position or para position. As you can imagine, with all those electron deficient function group here, this ring is not coordinated enough. They are not reactive. And we don't want to hit the ortho through the directing effect. We really want to avoid that. So how do we do that? The key idea is to come out with this ligand again. So let me walk you through the basic principle, how we came up with this ligand. We basically need a ligand that is very strongly coordinated to palladium, right? You need that. But that's a kind of problem. If you have two ligands both strongly coordinated to palladium, then where does the substrate come in? You have no space. That's one problem. But you do need the ligand to be coordinated to the palladium all the time. So what we did is keep the alpha position, the carbon 1, with minimum sterics. So the coordination one-on-one is very strong, and you can measure that bond distance. But on the other hand, if the second ligand dare to come in, then we build up the sterics from the remote side, then they start to repel. We call this mutually repulsive only ligands, okay? And how do we know that's working? We actually made the crystal structure at 0 degree. Sometimes it's just amazing that what students can do. I would never be able to do that. They were able to get a crystal structure of this at 0 degree, and they show me that when you warm up to room temperature, following by NMR, the other ligand will be kicked out, and the substrate actually can displace this ligand, come in to form this precursor. And as you can see, the ortho CH bond is blocked because of the sterics. Now you cleave the metal CH bond, and bingo. So I'm not saying we have solved this problem because the selectivity is only 80%, but I think we made a big dent on this, untouchable problem basically. But once you go to industry consult, you realize what they even want more is pyridine. Pyridine is a $1 million problem because in drugs, in cleavage, right, it's a huge problem in cleavage library synthesis for cancer drug molecule. You just can't have it. In many chemical space, you cannot make in large quantity. The simple reason is the C3 is very hard to do. Well, before C2 cannot be done very well, but Phil Barron solved that problem last year. But now the C2 still is a big problem, right? So how do we develop a catalyst? The big problem with metal is almost any metal would coordinate to the nitrogen, and that's the end of the catalysis. You cannot reach the metal. So we decided, let's not worry about the catalysis. Let's just worry about solving this basic problem. How do we develop a ligand or catalyst that would actually not coordinate to the pyridine strongly, like a weak coordinating? Can we do that? And of course, with that mind focus, we were able to partially solve this problem by design a bis-dente pyridine ligand. We were able to kick this pyridine out through transient effect. And basically, this is coming backwards and forwards. But then, of course, the problem is if you kick the substrate out, that's not going to help. You cannot have reactivity, right? But remember, this pyridine will come back. And then if you think about the molecule as not stagnant as a dead molecule, but like a fish swimming in the pool, you can imagine when they're swimming back, they could make one mistake through the head, or not through the head, but through the tail, and you could catch the tail. And then that would, of course, that requires the palladium to be very hot and reactive, and that could cut the CH bond. And I will stop trying to convince you that idea is reasonable, but let me tell you the result. It works really well, okay? And the idea, in my opinion, the best way to convince you is this is like a fishing. If you do normal fish, you let the fish bite your fish hook, and that you will catch the ortho position like a strong directing group control. But if you do fly fish, what do? You let the molecule build up the local concentration around the fish hook, and then you fly them. You catch wherever the fat part of the fish. When I try to explain this idea to my colleague Julius Riebeck, he actually thought this is an obvious idea. Although before nobody thought I was correct. But when I explained to him, he said this is such an easy idea. It's a high effective molarity. So either way, we couldn't take too much credit. But the important thing is the idea works. Okay, the chemistry really works. And let me tell you, one step, we synthesized many drug molecules. Three of this are in clinical trial in the literature, and otherwise takes 8-10 steps to make. It's very difficult to make. And of course, this idea can also be extended to making bi-arrow molecule. The same idea, but you can make a bi-arrow, just CH bond cross-coupling to arrow bromo. And again, we made a 10-gram scale of this drug molecule in much shorter route. Okay, so let me then summarize what I have tried to really convince you so far is weak coordination is a magic concept in this area, and we really have to embrace this idea. Weak coordination is not weak, it's only psychologically weak. Physically, it's very strong, okay? And most importantly, we need to develop a ligand really to accelerate the CH elevation. But having said so far, I think I was kind of trying to be very positive, but let me tell you the truth. There are still so many challenges in the field, which is good maybe for science, but in the interest of time, let me just tell you one project that we are still having hard time, but we're beginning to making progress. Let me show you what is the problem. And that is the remote CH elevation. So far, you have seen phenylacetic acid as a very interesting backbone. Phenylethyl alcohol, we can finally do that. And we can also speak or listen to the substrate electronic effect, and we can design a ligand to match the selectivity, which all of those chemistry are great. But there are many scenarios we are hopeless in terms of when you really want to design a synthesis in an unreasonable way, so to speak. What about hydrocinamic acid? It's a very useful class of natural product or bulky chemicals, hydrocinamic acid. What we want to do is, what about if you just want to cleave the CH bond in the middle of a desert, in the middle of nowhere, right? Because the functional group is far away and it's hidden in an awkward position. Basically, what you want to do is you want the palladium to interact with the carbonyl in a weak coordination and somehow make a big U-turn to reach the CH bond in the metal position. And be careful when you make the U-turn, you cannot cut the corner. That would do the ortho CH activation. So it's quite a lot to ask. How do you do that? However, if you can do that, it would be great because then you can plan your synthesis in a very unusual way. What about overriding the electronic effect? If you have a mesoxy, that would go para. Can you do meta? If you have a CF3, that would go meta. Can you do para? To override the intrinsic substrate and then do whatever you want, basically, right? And of course, most importantly, can we achieve side selectivity? Meaning, if the CH bond is in totally different parts of the world in a molecule, can you still design a template, like a recognize through molecular recognition to reach certain CH bonds through just recognition to cut the CH bond? And all of this is made possible now. Let me explain to you how this works. So let me then translate all those problems. What is the fundamental problem? The fundamental problem is in the last 50 years, we have been pretty good at understanding to assemble a cyclic transition state. And usually it's a 6 to 7 member ring. What we are not good at, or we don't know how to do it, is cyclophane transition state, very highly strained. Although in Scripps, that synthetic chemistry has overcome that. Many groups, right, KC, Delborg, and Philband, they have all made extraordinary cyclophane structure, but that's a very challenging molecule. But in terms of transition state, in the catalytic sense, we really don't know how to do that. And especially macrocyclic ring. What about 12-member, 15-member ring cyclic transition state? We're not very good. How do we do that? If you just look at this structure, treat this structure as a stagnatic structure, all you get, if you look at it for 2 minutes, all you get is headache and losing confidence, really. And you can try. Okay, really doesn't make sense, this structure. But however, if you jump outside that box and forget about the molecule as a structure, instead treat them as a fish in the pond. They're swimming around dynamically. What you could then think about is perhaps we can link the substrate to the palladium somehow through a practical linkage and through the weak coordination. And the palladium will be on and off, on and off. The key is to build up, again, the local effective molarity through space, not through the structure, but through space. Then you hope you can have a ligand that make the palladium very hot. So if they touch it, they can cut the CH bond. That is the basic idea. But how do you translate this very vague idea into the reaction flux? In other words, how can I convince the student in the audience to take on this project and start to set up experiment? That is more difficult. And here you go. The idea is we decided to develop a template that's very flat. It's very important that this template is flat because then that would keep everything else that's attached to this flat template approximately in the same space, so to speak. Then what we do is attach the substrate through the protecting group again, Phil, I'm sorry, through the protecting group, the benzyl ether here. We then engineer weak coordination nitrile group to bring the palladium into the same quadrant. If you notice the blue dotted line, you have 1, 2, 3, 4. Now everything is in the fourth quadrant that matters. That's the basic idea, right? But that's not enough. What you really then you need is to engineer a linear coordination structure, nitrile, that would totally avoid reaching the ortho position. If you do that, that would have to bend the structure 60 degrees by computation study. If you reach the metal, that would be only 10 degrees. So it's much favored now. Surprisingly, through this structure design by model, by computation study, it's very clear that this design would favor the metal remote CH activation, on paper anyway. And this then, of course, takes 3 years, 2 postdocs. Wonderful student, Jackson, has just got an academic job in Singapore, and Gang Li is still here. Hopefully he will get a job soon. 2 postdocs, almost 3 years. They haven't published anything except solving this problem in the end. Almost magically, you can put on this template to a very simple arring. You can cross-couple to any double bond. And let me tell you, so far before, in this kind of a reaction, you cannot handle di-substituted or tri-substituted. It's only terminal. But now this reaction is even more powerful than the strong coordination substrate chemistry. You can start with trans, you get a cis. If you start with cis, you get a trans. So it's a stereoselective, stereospecific as well. And that's beautiful for synthetic applications. But of course, the key is can we then generalize this idea? Basically, what we want to develop almost a universal template that can work with any natural product. As long as you have any function group, can we do that? We then turned this idea into something slightly different by using this almost readily available amine we attach to hydrocyanic acid or any carboxylic acid. We were able still to reach the CH bond here. And that, again, is proven by the model, by computation model. Clearly, the palladium is making huge U-turn to reach over the CH bond selectively with 95 above selectivity. And of course, application has been immediately found. If you are interested in unnatural amino acid, this would be very interesting route. Actually, we are interested in making polymer. Through this monomer, we make a very interesting polymer with the covalent linked amino acid, and that will be used as a ligand for scale up. So that's a very interesting dimension that we're going to take within the NSF Center. And of course, drug discovery here. With this molecule, we can make a very unusual drug library in collaboration with BMS. We are very interested in making library from this kind of amino acid structure. And most importantly, we can also perform site-selective molecules, perhaps, like biphenyl. Again, biphenyl is everywhere in drug discovery, of course, but we are also interested in natural product synthesis and ligand synthesis using this technology. And the next level is, can we then do ketone, phenol, and even natural product? And I can tell you we have finished all of this, and it's all coming. This one is almost done. We're almost ready to submit, and this one is still in progress, but this one is done, basically. So that tells you there is still a lot of challenges, but it's impossible. If you really dare to challenge them, maybe the solution is somewhere hidden in a corner. And that is the most important message I want to share with the student. And finally, of course, most important, I want to thank a wonderful group of co-workers, and I don't think I can ever thank them enough. Really. I mean, it's just the dedication, the kindness, and the creativity. I can never thank them enough. I have been very lucky, I have to say. And I don't want to point any single name, but let me just point to 2 high school students I have worked with. And the reason for that is I'm a really big advocate that we need to cut the talent pool a little bit earlier for science. And that, I think, it could be a very effective tool. And the Scripps is doing very well. But also, for a selfish reason, I do want to use these 2 high school students who published 2 JACS papers with me to convince the industry that our chemistry is very easy to use. If high school students can do it, then maybe they can do it too, right? And of course, the funding agency, very important. And recently, we have actually just got approved phase 2 NSF Center grant, and Donna, of course, as a colleague, is also in the center, and I hope many other Scripps colleagues will be involved in the center as well. And it's a very, very interesting center towards future, development of a future technology based on CH activation. And finally, Phil, I must remember to get back to you on that introduction, okay? But thank you all for your kind introduction. But before I finish, let me also add that I want to take this opportunity to thank all my colleagues for their tremendous inspiration and kind friendship. Thank you so much.